Hi everyone, our notes today are for 4.2 and we have one main theorem here, which is the mean value theorem. Sorry, there we go. Mean value theorem, there's a couple other topics that come up as well, but the mean value theorem is of course the main topic. So we'll start with that. What is the mean value theorem? Well, the hypothesis is two-part. So in order to draw our conclusion, you have to satisfy these two things. So first of all, we have to be talking about a function that's continuous on a closed interval and differentiable on the open interval. So as long as we have a nice function that looks continuous on the closed interval and differentiable on the open interval, then we can draw this conclusion. And basically our conclusion is that there is well, I'll start with this part down here, that there is some point in that interval whose slope of the curve at that point is the same as the slope of the secant line between the two endpoints. So if you look at f of b minus f of a over b minus a, this is really just your Algebra 1 calculation of slope. And A and B are the endpoints of our interval. So you picture a line going through the endpoints of our interval. That line's slope is what we have on the right side. On the left side, this is the slope of our curve at a particular x value. So again, there's somewhere along my interval A to B that has a particular point, or maybe more than one, whose slope is the same as the slope of that secant line. Again, this is assuming the hypothesis is true. So you can consider it the tangent to the curve at the point being equal to the slope of it being equal to the slope of the secant line that goes through A and B. We've also talked about that tangent line as the instantaneous velocity or instantaneous slope, and over here the secant line would be the average slope over the interval. So again, the mean value theorem here is an existence theorem. It's just guaranteeing us that there is at least one place, which we'll call x equals c, where these slopes are equal. Okay, so let's try an example here. So this one says, show f satisfies the hypothesis of the mean value theorem on our closed interval 1 to 4, and find that spot C in the interval such that this is true. So here's our function that we're given. It's a cubic. And so first of all, does it satisfy the hypothesis? Well, you have to ask yourself, is it continuous on the closed interval? This is just a cubic. It's a nice polynomial. So yes, of course, it's continuous. And is it differentiable? Yes, there's no corner or cusp or anything weird, no points of discontinuities. So yes, our hypothesis is satisfied. So then find the value of c in the interval that this is true. So if I go ahead and compute the right side first, this is just my normal calculation of slope on the interval 1 to 4. So I plug that all in. And then on the left side is our derivative of our curve at some point c. And I set these things equal and solve. I get a plus or minus root 7. And because my interval was 1 to 4, negative root 7 is not in my interval. So I choose the positive root 7. And that's pretty much my x coordinate that would have the same slope as the secant line through the endpoints. Again, the x equals root 7 is the x coordinate of my tangent line that would be parallel to the secant line through AB. Okay, moving on. Increasing and decreasing functions. This one's an easy one, you guys. I think you already know it. If your derivative is positive, that means slope is positive, your function's increasing. Positive slope, function's going uphill. It's really that simple. If your derivative is negative, then your function is decreasing on that interval. So if we give a quick try here, here's my function. I just took a parabola. If I take the derivative of it, if I set it equal to 0 and solve, I get 3/4. So here at 3/4, when x is 3/4, my slope is 0. And then if I pick a number just to the left of 3/4, let's say 0, and I plug it into my slope, if I'm using my test point of 0, it would come out -9. So it would be negative. That means that on the interval to the left of 3/4, my function will be decreasing. My parabola is going downhill. And then at 3/4, that would be the vertex or the minimum of my parabola. And then after 3/4, guess what? It turns around, it goes back up. You could pick another test value, let's say like 1. If I plug in 1 for x, 12 times 1 minus 9 is positive. So I know after 3/4, my parabola is going back uphill, it's increasing. So we would say it's increasing on the interval where x is less than -3/4 and increasing when x is greater than 3/4. So that's a nice simple concept you have to look at tonight. Antiderivative shows up for the first time as well. I put over here my little note, heavy foreshadowing of an integral. An antiderivative is basically the opposite of taking the derivative, which is an integral. So up here in the blue box, I put up here just to kind of get your mind thinking, if I gave you this equation here and asked you to take its derivative, you'd get 12x squared. Now if I give you this equation, notice that the constant on the end is different, and yet the derivative, amazing, is the same thing. Okay, so if we're trying to work toward integration, ultimately in Chapter 5, then we have to be able to look at the derivatives equation and say what the original function is. We're just going backwards when we integrate or find the antiderivative. Okay, so if we know that the derivative is 12x squared, can we predict then or find out that y is this equation or this equation? Well, if I don't have any other information, all I know for y is that it would be 4x cubed plus some sort of constant. There's no way to really know whether it's a 2 or a 1 or something else. So the antiderivative would be something in this format where there's some constant on the end, and I would need more information to figure out what that value is. Now, how did I get the 4x cubed? I know we haven't practiced this, but you got to think opposite of power rule. So instead of subtracting 1 from the exponent with power rule, you're going to add 1 to the exponent, so the x squared must have been x cubed before when you took the derivative. And then this coefficient 12, well, you're going to have to divide it by the new exponent. So 12 divided by 3 would give you the 4. So you do this enough times, you get kind of good at it, but first few times maybe you're rusty at it. So again, your process for undoing power rule, you add 1 to the exponent and you divide the coefficient by that new exponent, the 3 in this case. Okay, so the directions for this example, it says find the function with the given derivative whose graph passes through the point P. Okay, so for this problem here, they give us not just the derivative equation, but also the point P. So I know I look at my derivative like this. I try to do the opposite of power rule, so I'm going to add 1 to the exponent, giving me x to the positive 1/4. And then I divide the current coefficient by the new exponent of a 4th, which means a 4th divided by 4th gives me a 1. And then I add in my constant, which I don't really know what it is as of yet. But because they gave me some extra information about a point that the original function passes through, I know that this equation, I have an xy coordinate that I can plug in and solve for c. So when x is 1, y is -2, I can figure out how much c is, and I can write out my function's equation. Okay, hopefully that made sense. So here we have a couple practice problems. As usual, give them a try, hit pause, and I have the answers on the next couple slides. Okay, let me read it first. So the first one, find the local extrema and where the function increases and decreases. Okay, so just adding the increasing and decreasing compared to the previous section of homework. So the same thing as before, to find the local extrema, and then talk about increasing and decreasing. Okay, so first things first, I went ahead and distributed my x to the 1/3 just to do a little algebra there. It made my derivative easier to compute just with power rule instead of having to do a product. I like power rule more, so I just did that for my derivative. And then the same little chart that I like to use to keep things organized, I'm going to consider my critical numbers and any endpoints. Of course, on this function, there are no endpoints. So my critical numbers are any values of x that make the derivative 0 or make the derivative not exist. So I took my derivative and set it equal to 0. I kind of cleaned it up a little bit and solved, and I got -2. And so f of -2, whatever that y coordinate comes out, is my global minimum. Now, how do I know that it's a minimum, not a maximum? Well, I don't really know yet, but I graphed it. I kind of cheated and graphed my picture, and I could tell when x is -2, whatever that y coordinate is down there, that's got to be a minimum. When the derivative does not exist, Well, again, looking at this negative exponent, that means my x is in the denominator. I'm not allowed to divide by 0, so if x is 0, my derivative is not defined. So when I look at my picture, x equals 0, it looks like I have a vertical tangent there. Again, a little reminder, places where the derivative does not exist would be corners, cusps, vertical tangents, and of course anywhere that the function is not continuous. Okay, so this happens to be a vertical tangent case. So at this point, when I'm looking at my graph, I really only have one extrema, and that is going to be whatever the y-coordinate is when x is -2. So my critical numbers are -2 and 0, and my extreme value, I just have 1, would be whatever the y-coordinate is when I plug in -2. I guess I was too lazy to do that. Okay, the other part of the question then, the new part for the current section, is this increasing and decreasing idea. Now, in order to kind of organize things, I decided to do this little number line down here and put all of my critical points that turned up on the number line. If I had endpoints, this problem I don't, but if I had any, I would put them on my little number line as well, just to make sure I'm not bothering to look at any numbers outside of my interval. Okay, so for this one I just have the -2 and 0 as my critical numbers that came up. I'm going to go ahead and check and see what my slope is to the left of -2, in between -2 and 0, and to the right of 0. So first of all, checking to the left of -2, you can pick any number you want to the left. Let's say -10. I don't know, something kind of obvious. Hopefully it's clear that it's negative or positive. So if I plug in to my derivative equation a -10, this part here is negative. This part here, well, because it's a squared, I know it's in the denominator, but it's squared there, it's got to be a positive number. So the question is, which one is bigger, the 4/3 times -10's cube root, or the 8/3 times -10 to the -2/3. So I guess that's a little hard to compute, but if you work it out, it does come out a negative number. If I plug in a number in between -2 and 0, like let's say just -1, plug that one in, that's a little quicker to see, it does come out to be a positive number. And of course, if I plug in a positive number, I'm adding two positive numbers, it better come out positive. So when I've got my little chart made here, my little number line chart, it's real easy to see then that my function must be decreasing because the slope is negative on the interval up until -2, and the function must be increasing on the interval from -2 to 0, and again increasing on the interval from 0 to infinity. Remember, at 0 the function, the derivative does not exist, so I kind of leave that out of my interval with the parentheses instead of a square bracket there. And -2, remember, that's just the absolute minimum of my picture there, so it's going to be decreasing up until then. Interesting question in case you're wondering about this closed bracket versus open bracket with our interval notation. You know, -2, is that considered part of the interval that's decreasing, part of the interval that's increasing, or both, or neither? The good news is on the AP exam, they're not going to care whether you include -2 itself or not, as long as you're very clear that at -2 that this slope is 0 and the function has a minimum there, a global minimum. So they're not going to really care whether or not you choose to put a square bracket or a parentheses right here and also right here. Same thing with the 0. Okay, so they're just concerned that you're looking at an interval up until then. Whether you include it or not a big deal. Okay, so the second problem, let me go back and look at the question here. So write the equation of the secant line AB and the tangent line that's parallel to AB. So if I go ahead and take a look at my picture here, so I just have my usual square root graph but shifted to the right by 1. So it's a little hard to see, I got a lot going on, but this black curve through here would be my function that I'm starting with, and I'm trying to trap it in the interval from 1 to 3. So I just have this one section here in black from x equals 1 to x equals 3. So the question is, if you draw a secant line that goes through the endpoints 1 and 3, which is my blue line, what is its equation? Okay, you guys, that is an Algebra 1 problem, practically. To calculate the slope of that blue line, that's this part here, f of b minus f of a, or b minus a. Just plug it in, you get your slope. And to write the equation of a line, Let's hope you guys can do that. You plug your slope in, and then you need just any point that you know of on that line. I chose this point right here because it's so simple, which would be 1, 0. Plug in 1 for x and 0 for y, and there it is in blue. Now, the question is also to find the equation of the line that is parallel to it and tangent to the curve at some point. So again, equation of a line tangent to the curve. Well, because it's parallel, I know the slope better be the same as before, root 2 over 2. But this time, the values here in red, the xy coordinates, I don't know of any point for sure that's on that purple line. So I don't know what to plug in for my x1, y1 yet. So these red numbers actually come from down here. So I got to go through this part. So that's where my mean value theorem comes in. It says that as long as my function is continuous on the closed interval, which it is, and differentiable on the open interval, which it is, then there's some point C that has the same slope as the slope of the blue line. And so the slope of my curve at that point has to equal the slope of the line that's tangent, that's secant through the endpoints. So I already calculated the slope over here, root 2 over 2, so that's this number on the right, and then my derivative goes in on the left. So just take the derivative, here it is. And I solve this out, and x comes out 3/2. So if I look at my picture, 3/2 is 1.5, that looks about right. This is my point of tangency, the point where the slope of my curve is equal to root 2 over 2. Okay, so I went ahead and plugged in my 3 over 2 for x into my original function to get the y coordinate. And here I have a point xy that's on my tangent line. All right, that is it. By the way, I guess my concluding part here is this section, really important. This mean value theorem, for sure you need to know it for your AP exam. So look at it again and again until it clicks and makes sense. This picture probably is the best way to clearly understand what's going on, at least if you're a visual person. And also this idea of increasing and decreasing, being able to do this little number line with the pluses and minuses for the derivative and drawing the correct conclusion about where it's going up and down, for sure on your AP exam. Okay, I will see you guys next time.